All right, AP. We are going to talk about a little thing called entropy today. Okay, may have already heard of it. Entropy is a factor of thermodynamics. I know it's a very fun topic to hear about, but let's see if I can spell this right. Thermodynamics. There we go. Okay, it's a factor in thermodynamics. Okay, we've already talked about enthalpy. Okay, and that is the exchange of heat energy. Okay, entropy is a little bit more abstract to talk about. There's a couple ways that you can think about entropy itself. Entropy, goodness gracious, entropy can be thought of as chaos. Okay, now this is probably one of the easier ways to think about it just abstractly. And the general sense is that the universe generally wants to expand the chaos. Okay? This is an easier way to try kind of understand it. It's not necessarily the correct way to think about it. However, it is very easy to understand. It's very easy to think about. It's very easy to just sort of very easy to just sort of rationalize in your own brain. So if we think about a situation where we have two bulbs. I should probably draw this bigger. All right, we got bulb number one, and it is attached by a little column, or row if you want to call it that, to another bulb. Okay, and there is a stopcock here. Okay, funny word, easy meaning, just means it sections off the two bulbs. Okay, one bulb has a bunch of ideal gases in it. Okay, let's see, how many do I have there? 8. Okay, let's say we have 8 gas particles, 8 moles of gas particles in there. Okay, and the stopcock is sectioning off, not allowing the gas particles to go over to the other side. Now, by laws of entropy, if we open the stopcock and release everything that's inside, we're going to see the gas particles start to transfer over to the other side until we get an even distribution of gas particles. Okay, now you might be thinking to yourself, Mr. Fry, I mean, why is that expanding the chaos? Okay, think about it as bouncy balls being bounced around inside a container. Okay, if a bouncy ball is in a small container and it's thrown and it starts bouncing, good amount of chaos, right? Now, if you are in a larger box and you start throwing the bouncy balls again, and it's going to start exploring and transferring its energy in a larger area. It's going to be bouncing off that wall, that wall, that wall, an extra wall here. And so the general chaos of those bouncy balls is going to increase. Okay, so that's something that is you can think about it as it's expanding the chaos. Another way to think about it is an ice cube. Let's see if I can draw an ice cube here. There we go. Okay. And it starts just normally starts to melt. Okay. Now, if you're thinking about a solid, something that has a very orderly particulate structure, and it goes to a liquid, which is less orderly, right? You're expanding the chaos. Okay, you're making those particles have more room to move, more freedom of movement, and so there's going to be more chaos involved. That is why it is more favorable in the universe for ice to melt than it is to stay as ice. Okay, that's part of the reasons. There's many different reasons, but that's part of the reason. Okay. It is also the reason why if you have a glass of water in your house right now, and it is you drink all of it, but there's those little drops that are left over uh, in the bottom. Okay, you leave that out in your counter or on your nightstand or whatever. Those droplets are going to evaporate until there is nothing left. Okay, they're going to evaporate into a gas. Okay, now, did we increase the temperature of the room to get to the boiling point of water? No. If you're staying in a 100-degree room, that would be a sauna. Okay, that would be awful. You'd be sweating your butt off. So, what happened is that it is more favorable than water being in a liquid. It's more favorable to have more chaos, more energy, more room to move around as a gas. Okay? So that's the sort of easy way to sort of comprehend entropy for people, especially that do not like math. Okay? I wasn't a huge math fan, so it's easy for me to think about entropy in terms of will it expand chaos? Now, another way to think about it is in terms of probability. Oof. You can tell I was a chemistry major. Probability. There we go. You can think about it in terms of probability. Now, any event that has a high probability, oh my goodness, probability, there we go, probability of happening is a more entropic, I don't know if that's an actual word, but entropic situation. Okay, let's go back to our bulbs. Now, let's say we've got bulb number 1 transferred, bulb number 2, and we've got 4 gas particles in there. So we've got a blue one, we've got a purple one, we've got a red one, and we've got a lime green one. There we go. Easy to tell. And we've got a stopcock in there. Okay. Now, as soon as we remove that stopcock, let's think about the probability of these gas particles spreading out and being evenly distributed. Okay. So let's start doing a probability tree here. We could have all the situations where we have 2 gas particles in each bulb. Let's do that. We've got a probability of I need to draw smaller for these. So this one, bold 2, transfer, and we've got blue and purple, and then red and green. Okay, boom, evenly distributed. But it could also be, I need to draw a little bit bigger there. That's probably better. Could be blue and green. It could also be red and purple on the right side. Okay. Could also be a number of different situations here. I'm going to draw just a few more here so I can quickly go through. It could be red and blue, and then purple and green. And I believe it's hard to think of all these situations. It could be, let's say, purple and is there one that purple has not been matched up with yet? Purple and red, purple and green, purple and blue. No, there isn't. So it could then be, can you erase? No, we'll just leave it. It could be purple and green on the left side, and then red and blue on the right side. It could be purple and blue on the left side, and red and green on the left side. I don't know if I said left on the last one, but you know what I mean. And then it could also be, there's one more, red and blue on the right side, and purple and green on the left side. So these are all the possibilities of the gas particles being evenly distributed. Okay, 2 on the left, 2 on the right. Okay, now let's think about all the possibilities of just having 3 on one side and 1 on the other. We would have, let's say 1, 2, let's say we've got blue, purple, and green, and then red on the right side. And then we can have green, red, and I feel like I'm missing a few. I got it. I know where I went wrong. I'm going to keep going. We can have, and then blue, and then that would mean that purple is on the right side. And then we can have, finally, blue, and actually there's 4. There's one more. Green. Okay, so that's all the different ones that can be just on the right side by themselves. And then add that one, and that would mean that we'd have blue, red, and purple. And then it'd be green, purple, and red. All right. At this time, I'm going to do some internet editing, video editing magic. And when we come back, it's going to be the probability tree is going to be completely filled out. Okay? Okay. So, video magic. We've got the rest of the probability tree here. So, on the right side of the column over here, it is when we have 3 particles on the left and one particle on the right. So there's four different probabilities there. And then right here, we have the probability of all the particles staying on the left side. Okay. Secondly, we've got on the other side, we've got all the particles being on, or we got three particles being on the left or on the right side. Goodness, on the right side, and one particle being on the left side. So there's four probabilities for that happening, and where all the particles then shift from the left to the right and stay there, that is one probability. Okay. Now, why is it more favored for the gas particles to be evenly distributed between the left and the right bulb? It is because there is more probability, more entropy in this situation. Okay, there are more probability and more chances of that actually happening. So that is the other way of thinking about entropy. Which one is the higher probability of happening? All right, so let's go through and think about some of the rules for determining higher or lower entropy. One, if things get dispersed into a larger area, entropy increases. If things dissolve or change from solid going to a gas or a liquid. So anywhere in that journey, things increase in entropy. 3, the more complex the compound / lattice, the higher there we go, higher the entropy. Finally, 4, if a reaction produces more moles than originally present, entropy increases. Okay, so these are 4 different sort of, not rules, but sort of guidelines to determine if a situation will increase or decrease in entropy. Okay, reminder, entropy can be thought of as probability or as chaos. Okay, generally the universe wants to create more entropy, so increase the amount of entropy. So natural things that are going to happen are things that are going to increase the entropy of the situation. Okay, we'd had an example of ice melting, water evaporating out of the cup at room temperature, things like that. Okay, and then remember the gas particle probability tree. Okay, you can think of it as a little probability graph right there. Peak probability right there, right here. Okay, so that is entropy. It is a very long video. I apologize for that. However, it is a very complex topic. I want you guys, the viewers, to sort of comment below on the video what you think a situation in your everyday life would be of increase or decrease of entropy. Okay. Have a good day, stay healthy, and I will see you guys in the next video.